and he'll be talking to us regarding glasses and other amorphous solids. As a customary, I'll introduce Professor Sastry, who is a professor at the Jawaharlal Nehru Centre for Advanced Scientific Research, Bengaluru. His research interest lies in the area of statistical mechanics, with a focus on understanding a range of unusual and interesting properties of liquids and other soft condensed matter, addressed with computation as a major tool. His significant research contributions involve the exploration of the energy landscape approach to glass-forming liquids, analysis of fragility, the rapidity of the change of dynamics of glass formers, length scales relevant to slow relaxation, glass forming ability in jamming, mechanical behavior, and memory in amorphous solids, anomalous behavior of water, liquid-liquid phase in transition in water, and so on. Professor Sastry has received many awards and accolades, including J.C. Bose National Research Fellowship in 2015, Shanti Swarup Bhatnagar Award in 2008, Sir C.V. Raman Young Scientist Award by the Karnataka State Council for Science and Technology, Swarnajayanti Fellowship in 2003, Birla Science Prize in 2001, and Professor C.N.R. Rao Oration Award in 2001. With these words, I request Professor Sastry to kindly share his screen.
Do you see the screen?
Yeah, absolutely fine, sir.
So ready when you tell me.
Yeah, please go ahead, sir.
Okay. Thank you, Dr. Saxena, and the organizers of this series of lectures. I hope I'm audible. If I speak louder, please tell me. Yeah, so I heard the second half of the previous talk, and I'm feeling a little hesitant in giving mine. There were a lot of very interesting and very important issues that were covered by Professor Singhi, some of which will recur in my talk as examples here and there. So I hope you can make the connection. Let me start with some very general thoughts. You know, when we look at what kinds of science is interesting, one can sort of easily relate to two kinds of sciences, which I call here fundamental science and applications. Fundamental science, various kinds of origin issues, origin of the universe, origin of life, fundamental particles, forces, etc. And most of us have an appreciation for why those are important and interesting things. And at the other end of the spectrum, you have applied science, where you make something out of the scientific knowledge that you have. And this too is clearly understood by the majority of people. But what's sort of not well placed and appreciated is in fact a very vast stretch of things in between, which I want to call the physics of emergent phenomena. I use physics because most of what I'm going to be talking about is physics, but it's physics and other branches of science as it applies to emergent phenomena. In fact, a very obvious example that might spring to mind is life processes, which are not particularly a domain of physics. This intermediate regime is something that encompasses the processes and things that make up most of the world as we experience it. And in fact, when it is at least pointed out, one can understand why that's an equally fascinating third domain of science. but it's a domain that is connected with the other two that I mentioned, namely fundamental science and applications, in very interesting and important ways. The first is that by looking at the physics of emergent phenomena, one very often comes across new principles that are not anticipated by fundamental science. I'll say a little bit about it in the next slide. And the other, of course, is that the same kind of investigations form the basis for imagining applied science. Okay. So the first point that I mentioned, that by looking at this middle kingdom, so to speak, one comes up with new principles that one may construe as fundamental, was articulated by famous physicist P.W. Anderson. And among other reasons, I sort of mentioned this also as a commemoration. He passed away earlier this year. And back in the early 70s, Anderson wrote a very important and influential article whose title is probably very familiar to many, which says, "More is different." And the argument that he made is that when we look at different levels of organization of physical matter, we cannot simply think of a larger scale organization of matter as sort of a subject of simply applying fundamental laws and rules that apply at a more microscopic level. So in fact, he sort of says, if you look at solid state physics, which is made up of atoms and electrons, which in turn are made up of fundamental particles, quarks, and so on, you cannot simply say that solid state physics is applied elementary particle physics. He makes the argument that at different levels of organization of matter, there are, it's at least not useful to think of it as simply a domain for application of laws that are known at a different level, but there are new laws that emerge at these different levels. Okay, and by now, this is a very well understood and appreciated idea. And so this is sort of an explanation of the first point that I made, that that by looking at the physics of emergent phenomena, one discovers new fundamental laws and knowledge, which is not apparent when one looks at a more microscopic description of nature. As I go along, I'll at least hint at a little bit of the second point of how our sort of attempt to understand the properties of matter at different scales of organization has implications for applications and applied science. But I will mostly be, just to make the point clear, where I come from, I try to understand the properties of matter in this middle domain of emergent behavior. Okay, and what exactly that is will become clear as we go along. So broadly speaking, the kind of things that we look at fall under the heading of condensed matter. So I want to say a little bit about what that means. Okay, it doesn't bear repetition that everything around us is made up of large assemblies of atoms and molecules. We study it in high school these days. And there are different classes of matter. So the ones where the constituent atoms or molecules interact strongly with each other, and these interactions form the basis of their properties, broadly solids and liquids, are referred to as condensed matter. And of course, solids and liquids sounds boring, but there's a very wide and rich diversity of what goes under this heading, some of which will become clear. And this is sort of the type of the class of materials that we talk about when we say condensed matter. And there's again a staggering diversity of properties that one may be interested in. So I give some examples here: electronic properties, magnetic properties, mechanical behavior, how something might flow. This is the field of rheology, etc., etc. And the list is fairly large, but it does belong to certain sort of basic themes. I list some of them below. So one basic theme in looking at condensed matter is phases and phase transitions. Properties of materials depend dramatically on which equilibrium thermodynamic state of phase this material is in. And again, the simple examples of solids and liquids make the point abundantly clear. And another kind of general theme that we're interested in is response to applied forces and fields. So if you look at a variety of what we are interested in, we're interested in knowing what happens if I do something to a given substance or material. And it's therefore a very significant paradigm of how we try to think of understanding something. Okay, so I said phases and phase transitions, and I talked about equilibrium thermodynamics, but the bulk of my talk is going to be about materials that in fact don't exist in equilibrium states. So there are, in fact, again, a very wide variety of natural and man-made substances which end up in different states depending on what exactly happened to them. Okay, and this is sort of not the subject of textbook physics, because in textbook physics, as I said, you say water at 300 Kelvin and 1 atmospheric pressure is a liquid in equilibrium. And water at minus 10 degrees Celsius at atmospheric pressure is in equilibrium a solid called ice. And that's what we try to, in fact, even in sort of advanced levels of physics, what we spend a lot of time on is trying to understand this kind of equilibrium behavior. But glasses and granular matter, which I won't really talk about, I had in mind to say something, illustrate this other class of materials, which are in fact very widespread, where their properties do depend on their history and how I prepared them and so on. And a key property of such materials is the presence of some kind of disorder. And many consequences arise from this presence of disorder. I'll say a little bit more. Okay, I already said that a large array of natural world and man-made materials belong in this category, and I'll give you examples. And something that more particularly in the context of solids, something that's interesting and not completely well understood is when you look at disordered or amorphous solids, they possess properties that are often significantly different from crystals, and I will say something about it later on. Okay, so here is sort of a collage of different images of glasses. Okay, I won't explain all of this right now because I'll take them case by case and I'll say something about it shortly. But before I do that, let me give you a sort of a one-line definition of what I mean by a glass. As I already said, a glass is an amorphous solid. And something that will come up again is that it's something that it's an amorphous solid that's typically reached by rapidly cooling a liquid. Okay, and how is it different from solids that we're normally familiar with, namely crystalline solids, is illustrated in this cartoon, where on the left-hand side, I have a two-dimensional cartoon diagram of silica. What you see is that in this crystalline solid, the atoms, two types of atoms in this case, are organized in some very regular fashion. There is what we call translational symmetry, and this is associated with key properties of the solid state, one of which is that this translational symmetry or broken continuous translational symmetry is associated with the rigidity of these materials. Now, in contrast, when you look at a microscopic view of a liquid, it has disordered structure. And liquids, by definition, are things that flow when you apply forces on them. Glasses are something in between. They have disordered structure, but they are rigid. And how this rigidity arises is something that forms a very fundamental and ill-understood question. Okay. Okay. Now, let me go through the examples that I mentioned in the first slide. One example, which is perhaps the most abundant, is amorphous water, which is found in cometary tails. And so, in fact, much of the water in the universe may be in this amorphous solid form. And another example is certain types of volcanic rocks, which is again, I mean, it's not all volcanic rocks are glassy, but obsidian, for example, is frequently found and much sought after volcanic rock. And it was sought after in earlier days because you could actually polish them and sharpen them very, very fine, as opposed to other materials, because crystalline materials often crack and break at grain boundaries. And volcanic rock, on the other hand, being a glass, does not have grain boundaries and therefore can be sharpened much, much finer. So this was used in surgical scalpels and so on. Another sort of somewhat funny and curious example is water within the bodies of animals under extreme conditions. So I give here a picture of an Arctic frog, and something that some of you might know is if the water inside a living body freezes into ice, it basically kills that animal or whatever living object. But if the same water freezes not into ice but into a glassy form, then the animal can survive. And this is in fact used by creatures such as the Arctic frog to survive in extreme weather. Okay, so glass is good for life. Okay, so here again, I now give a set of examples of glasses that we know from from man-made materials, oxide glasses in a whole variety of contexts, from high-tech to very low-tech, such as cooking vessels, fiber optics to glassware, is a very large range of glassy materials that are used. And there are also a number of other kinds of materials, chalcogenide glasses, which are used in memory devices, metallic glasses, which I'll say a little bit more about in a minute, polymer glasses, etc., etc. And humans have been making glasses for a long time. So here are a few sort of snapshots in India, in a place called Arikamedu down in the south and Takshashila in the north. glasses, people have discovered artifacts which were glasses. And through the medieval times in Europe and in India, glassware of various kinds was very popular, and glass tools, etc. And down to the present day. Here is a modern example of metallic glass, and I want to sort of use this video illustration to make a basic, an important point. So what you see is two balls. One is made up of titanium and crystal, and the other is a metallic glass. And what you find is that the metallic glass bead bounces up and down for a much, much longer time. This has something to do with the fact that this material has a greater ability to withstand deformations, plastic deformations to be precise. And these deformations, in fact, are what make ordinary crystalline metals useful, because you can bend them without breaking them. But there are situations where you don't want them to bend and dissipate energy. So here is an example of, you know, that distinction. And there are many applications such as MEMS that I mentioned earlier, and also in making sort of high-tech sports equipment and so on, where metallic glasses become preferred because of this property. So here's a slightly more technical view of this. What you're seeing is something that you're going to see again and again, which is a stress-strain diagram. So you can think of strain as some kind of a deformation, elongation, for example, and stress is some kind of force. The exact definitions I won't bother you with. And elastic materials have a linear relationship with these. You can have Hookean behavior, where the more you elongate, the force increases proportionally. And this kind of elastic behavior is seen by all solid materials for small enough deformations. But if you go to higher deformations, you have deviations from elastic behavior as a result of what are called plastic rearrangements, which I won't say much about, but this is fundamental. And what the graph on the left illustrates is that amorphous solids of a certain kind can have a much bigger elastic range as compared to their crystalline counterparts. Okay, so this is a very interesting property, but it comes at a price because metallic glasses exhibit brittle behavior accompanied by something called shear localization, which in the micrographs that I show, you can see as these bands that are disappearing, that appear, these almost straight lines, which correspond to places where the material, loosely speaking, cracked, okay? And this is not good for material applications. Of course, this happens at very large deformations compared to other materials of choice, but you still don't want things to break in this way, okay? So how do we make something which will not show this behavior? Is something that's good to know from a materials design point of view, but it turns out, as I'm going to illustrate as I go along, the basic physics of what controls this kind of behavior is only sort of slowly emerging in recent years. And we are still sort of working on having a theory of when a glass might behave in this brittle fashion versus not, okay? So that's where the kind of research I'm going to present to you comes into the picture, okay? Of course, you might be thinking, don't all glasses break in a brittle way? And that's actually true if you're only thinking of oxide glasses, the glass of ordinary experience. But in fact, there's a whole variety of materials that can form glasses, okay? And this happens on very different scales of the size of the constituent particles. On the extreme left, you have metallic glasses and silicate glasses, where the constituent particles are angstrom-sized atoms. But you can also make glasses out of colloidal particles, and colloids are micron-sized. But you can also make, at a slightly larger length scale, emulsions and foams, where the fundamental or the basic units of the assemblies, so in the case of emulsions, these would be tiny droplets that are stabilized. And those can be millimeter sized. And going up further, you have granular matter, such as a bowl of cereals that you see on the right-hand side. And this also can, under certain circumstances, behave like a glass. And the particles that make up this assembly are centimeter scale. Okay, so there's a wide range of particles out of which you can make solids, and in particular amorphous solids, and not all of them behave in the same way as window glass. Okay, so when a certain kind of glass behaves in a brittle way, when it behaves in a ductile way, is something that people would like to understand. Okay, now one thing I forgot to mention is that this expanded range of examples that I showed you here is is something that goes beyond what we might refer to as molecular glasses, atomic and molecular glasses, such as metallic and silicate glasses. And this range of solids, many of them are soft solids, they belong to a category of matter called soft matter. Okay, the exact definition I will not try to give you, but these are basically materials that deform by significant amounts with an application of small forces. Okay, the toothpaste that you see is an everyday example. Toothpaste will sort of look like and behave like a solid, but under very, very small forces, it will flow. And this is something that you want, and you want to be able to control exactly how much force you need to apply for the toothpaste to come out of the tube. So this is a fairly big area of research, trying to understand the solidity and rheology of soft materials. So that sort of expands the range of glasses that one talks about quite a bit. But there are also other kinds, and I won't go through a lot of boring examples, but I'll mention one important class of glassy materials that has played a very significant role in the conceptual development of understanding of these. These are called spin glasses, and these are basically disordered magnets where the interactions between spins can take either positive or negative signs. So in other words, there could be pairs of spins that want to line up parallel to each other, and there could be pairs of spins that line up anti-parallel to each other. These are called ferromagnetic and antiferromagnetic interactions. And when you have a triangle of such spins, two pairs of which have ferromagnetic interactions and one pair has antiferromagnetic interaction, you end up in a situation that's called frustration. The one of the spins doesn't know whether to point up or point down because both are equally bad. Okay, and this leads to a lot of dramatic consequences. One is that there are going to be a large number of states or configurations of spins that are equivalent. And these are called metastable states in a certain context. And it also leads to this notion of complex landscapes. and I won't again have a lot of, I won't have time to sort of talk about this at length, but the basic idea is that if I have these kind of disordered interactions, they're going to be a large number of local minima of energy or free energy, if, again, without elaborating, where the system can be mechanically or thermodynamically stable, unlike a simple situation where we might imagine that there's only one, for example, thermodynamically stable state. Okay, so the picture on the right-hand side is an illustration of this idea. It's not really a very useful illustration, but that's all you can manage in one dimensions in a one by one, when you have only one x-axis and one y-axis. But you have to imagine that this in a very large dimensional space to come closer to what people think about. Okay, but the basic idea is the presence of many local minima of some kind of energy. Okay, and now this is of course a valid picture for molecular glasses that I talked about earlier, as well as spin glasses. And in fact, the cartoon that I'm showing here is from some review article about structural or molecular glasses rather than spin glasses. But these kind of conceptual notions and tools actually carry to a very broad range of subjects. So one thing that may be of topical interest is neural networks and other forms of machine learning, where you try to optimize some kind of a cost function, and the kind of picture that emerges of how these cost function landscape might look is very similar to what one thinks about in glassy systems. So glassy concepts, though not obvious, have a very wide currency in physics and applied mathematics. Okay, now coming more precisely to the particular issue that I described earlier, which is mechanical behavior and possible failure of glasses. Once again, one can think about it in a very specific context like metallic glasses, but the same ideas carry over to a whole host of phenomena at very different length scales. And here are a couple of examples that may relate to the previous talk. Mudslides is something that one worries about in many parts of the world. If you think about it, depending on sort of the granularity at which you think about the system, it is very much like a glass that is failing, okay, because these are disordered assemblies of particles. And so there are a lot of analogies. Of course, there are differences because in mudslides, there is a fluid that embeds all the particles that you're worried about. And so there are additional complexities of the physics. But to a first approximation, you can think of it as a problem of plasticity in glasses. Okay, similarly, earthquakes, avalanches, and so on. So I won't go through the examples. But this is just to give you an idea that whatever I'm talking about, even though I will talk about it in a very specific context, can be and in fact are very much used in a wide variety of phenomena. Okay, all right. So, so some basic features of glasses so far. Glasses are widely found in nature and among man-made materials. I made that point. They're also mostly made of silica, but can be made out of many other things. This is something that's not common knowledge. So in fact, any substance can form a glass under suitable conditions. They can have interesting properties, which depend on how they're prepared. I haven't illustrated this yet, but I'll come to that. And how they respond to external applied forces is important to understand, as I already mentioned. Now, I want to say a little bit more about what is interesting about all this. So this is just in some sense, a recap of things I've already said. Matter exists in many phases, and properties of substances depend on the phase in which they exist. This is all textbook, high school textbook stuff. And so therefore, one can say phase behavior is an essential part of understanding a material. And in some cases, it can be pretty complex. And as an example, I show you the phase diagram on the right side of water. And by the way, can you see the cursor move on my screen? Dr. Saxena?
Yeah, we can see it.
You can see the cursor move.
Yes, absolutely.
Very good. And so what I show here is the phase diagram of water, which has many ice phases. Okay, this is probably not well known. So even for a simple material, the phase behavior can be complex, but it only describes the equilibrium state of matter. Okay, this is the point that I want to emphasize. Under given conditions, substances can exist in a diversity of other states than those dictated by equilibrium thermodynamics. And this arises as a consequence of what is called metastability and structural arrest, which is sort of a more complicated version. Okay, metastability is simple, and I want to illustrate this by looking at the phase diagram of carbon. And what I show here on the lower right panel is the phase diagram of carbon, and the blue area is the pressure and temperature regime, where diamond is the stable phase of carbon. Okay, but in fact, you know, diamonds are very much seen and are cherished under ambient conditions, which is way down here near the x-axis. And so even though the equilibrium phase of carbon is graphite under those conditions, thankfully, according to many, diamonds do persist. But, you know, they're under what are called metastable conditions. So if you wait for long enough, it'll convert to graphite. Right? Luckily for us, it's not a small amount of time that you have to wait. So effectively, diamonds are forever, but in reality, they're not. Okay. Now, the other kind of more complex metastability is what I call structural arrest or jamming. And this happens when matter gets stuck or trapped in non-equilibrium states that are long-lived. Glasses form a key example. And as I already mentioned, when this situation arises, the number of possible states in which a material can get stuck can be very large. And this is described by a technical term called complexity. And the presence of complexity also has very interesting consequences of memory effects as a result of the non-equilibrium state of matter that we're considering, and also very complex or slow dynamics. And I'll give you an illustration in a minute. So this is the domain of glassy behavior. Okay, it's much more complicated than metastability in the ordinary sense of diamond being metastable at ambient pressures. But it's a distant relative of this concept. So how do we describe jam states and transitions from jam states to flowing states, or vice versa, is sort of the broad question people worry about in talking about glasses. Okay. So here, let me start very simple. This is now a picture of temperature on the x-axis and volume or enthalpy, some property of a material on the y-axis. What is shown here is a red segment of the line which describes how that property would vary in the liquid state. Okay, but below some temperature called the melting temperature, you usually have a jump of that property. Let's say volume for the sake of concreteness. And because there is a phase transition to the crystal phase, and then I have a different temperature dependence below. But because of metastability that we already talked about, this liquid can go below the melting temperature but remain a liquid. And this is called a supercool liquid. And when a supercool liquid is cooled enough to sufficiently low temperatures, you undergo a second transition, which is called the glass transition, which is not a transition in the same sense. And what kind of a transition it is a fundamental question that many theorists at least work on. And that through the glass transition, you form an amorphous solid, which is called a glass. And one of the key things to note about the glass transition is where it happens very much depends on how you prepared your system. So if you cool the liquid very, very fast, you form one glass that has a higher volume or lower density. But if you cool it slower, it forms a different glass. Okay, so this fact that the glass that you form depends on the method of preparation. It's not just a sort of experimental nuisance, which many times such things are, but it's a fundamental property of glasses. Okay, not only a simple quantity like volume does depend on how fast or slowly you cool, but many other properties of glasses depend on this history. And this is something that's sort of fundamental to glass science that people try to understand. Okay, this I won't spend too much time on, but one can't talk about glasses without saying something about the viscosity of liquids as you cool them down. But I'll basically leave it at saying it changes by huge amounts, many orders of magnitude. And there's an illustration here of what viscosity different materials. Viscosity is basically a property that tells you how easily a liquid flows. And by the time you cool a liquid down to the formation of glass, it changes from its value at normal conditions by 15 orders of magnitude. Okay, and so I think I'm running a little low on time, so I'll skip this fun experiment where a couple of groups actually have been running experiments for decades and decades, trying to see how viscous pitch is, and so they've been very, very patient. Okay, but only 9 drops of pitch have fallen so far in one of these experiments. Okay, okay, again, a quick recap. Glasses typically form out of supercooled liquids that become very viscous and stop flowing. They're characterized by slow dynamics, which I won't say much about. They are like metastable states in the as in the simple example of diamond, or but they are many possible microscopic structures, which corresponds to the property of complexity. And okay, so glasses form as a result of a liquid falling out of equilibrium, as it is described, and contains memory of the past history, but it can be usually very complex to decode. So having said all of these general considerations, let me focus now on an important problem of current interest, which is to understand how a glass yields or fails when forces are applied on it. Okay, and this problem is something that we work on, and there has been rather interesting progress in recent times, and it illustrates a lot of what I said so far. Okay, so here is sort of some basics. I'll be talking about strain and stress, and strain is basically some measure of how much you displace a solid or parts of a solid. So if I take this blue rectangle and deform it into this red parallelepiped, I've applied a certain amount of strain, and that quantity is calculated by looking at how much I slid the top layer by with respect to the bottom layer, divided by how far apart the top and the bottom layers are. And similarly, I'll be talking about, I'm sorry, I've mislabeled it here. This is called shear stress, which is, again, if I take this rectangle, I apply force on the top layer, and this top layer has a certain length or area. The force divided by that area is called shear stress. But in simple terms, we can think of these as measures of force and displacement, okay? And they behave in that way. And as I already mentioned, when I apply force on a solid, there is an elastic regime, and then there are departures from the elastic regime. And this departure is what we want to understand. How does it happen? Why does it happen? I won't be able to tell you all the things we understand about it and all the things we don't understand about it, which is probably a longer list, but I'll tell you some things, okay? Okay, so basically, if you look at any solid, maybe I'll say more as I go on. This is again sort of to give you a visual picture of why it's important. I've shown some of these things already. When a solid yields in one of many possible failure modes, the consequences are not pleasant. So you want to understand when and why it happens. And now, when it comes to crystalline materials, there is a certain language for understanding how plasticity and yielding happens. Okay. By the way, I haven't defined plasticity, but again, as a simple one-line definition, a plastic deformation is one which doesn't revert when I remove the force. So an elastic displacement is one that goes back to zero when I remove the externally applied force. A plastic displacement is one that does not become zero even when I remove the applied force. Okay. Now, in crystalline materials, there's a way of understanding this, which is in terms of the movement of what are called dislocations. These are defects in the crystal structure. And as this cartoon movie shows, these defects move in order to accommodate external forces. And that's how plasticity arises and yielding arises in crystalline solids. That's not the whole story, but that's a starting point upon which a lot of literature has been built. In the case of amorphous solids, we don't have regular translational order as you see in crystals, and correspondingly we don't have the equivalent of dislocation defects, right? So if we wanted to measure what we mean by defects in a glass, we have no idea. And this is a conceptual challenge. And further, if we want to understand plasticity and yielding in terms of some notion of defects, we also have no idea. And therefore, you know, the game is fairly wide open at this point. But some progress, as I said, has been made in recent years, which I'll share you a little bit of with you. Okay. Now, if I take a piece of glass and I applied force, as I illustrated before, what I see is beyond the elastic regime, at some point, if I keep the force high enough, I'll keep on deforming the material. Okay, this is what is called the flow regime, where the amount of deformation keeps on increasing without a corresponding increase in the force. Okay, but as the picture on the right here illustrates, when it comes to glasses, how exactly that happens depends very much on the glass that I'm talking about for the same substance, right? So here are two sort of glasses prepared with different protocols of the same substance on the computer in this case, and they behave very differently. And also more importantly, if I want to understand something about at what point did the material yield and start deforming in this elastoplastic way, I can't really put my finger anywhere. Okay, so these are things that we want to understand. And so one way in which we've been trying to do this is through computer simulations of a model glass, which is sort of, the details are given here, but ignore it if you don't have to know. Basically, what we do is we deform this glass, as the little movie shows on the right-hand side, back and forth. This is called cyclic shear or oscillatory shear. And we look at what happens to the material if we keep doing this many, many times, okay? And what we find is something very interesting. As you might expect, as I strain the material back and forth, the stress also will keep going back and forth. But the manner in which it does changes quite dramatically as I increase the amplitude of my strain deformation. And in fact, if I look at the maximum stress that I generate by deforming at a given amplitude, that maximum stress shows a discontinuous change, which allows us to characterize yielding in a very precise manner. Okay. Again, I'm sorry, I won't be able to explain all of this, but just to give you an impressionistic picture. Now, the other thing that's interesting is if I look at what happens to the energy of the glass as a function of the amplitude with which I strain it back and forth, something very curious happens. If I start from small amplitudes to large, the energy keeps going down. So you deform a glass back and forth and it becomes lower and lower in energy. But there is a point beyond which the trend reverses and the energy starts going up. And by ways in which I won't go into, we identify this as a very sharply defined yielding transition in these glasses. So what this graph here shows on the left-hand side is also what happens when we do this for two different glasses who have starting energies that are different, and they seem to behave in a quantitatively different way, but qualitatively roughly in the same fashion. Okay, but something very dramatic happens when we look at a much wider range of initial energies. Okay, the initial energies is roughly what I have at zero strain on this axis. Okay, so what happens when we look at glasses which are better and better annealed, so that they have lower and lower starting energies, is unlike the behavior that I described earlier, where with larger and larger amplitude straining, I go down in energy and then there comes a point where the energy starts going up. What we find is a qualitative change where up to some threshold amplitude of strain, nothing happens. The glass is perfectly happy. It goes back and forth elastically, and then there is a sudden discontinuous jump when the glass yields. Okay, so in some sense, I go from a continuous transition to a discontinuous transition at the point of yielding. And there is, if we think of the initial energy of the glass as some kind of a measure of disorder, there is a critical disorder across which this change of behavior takes place. Okay. Now, there are sort of ideas of how this kind of behavior might relate to behavior seen in disordered magnets, and for which the theory is developed much more elaborately, but I won't go into it except to point out that there are these interesting connections between something that on the face of it might look like a materials problem to something that is very much a fundamental problem in statistical physics. Okay, but what these results lead to is a picture where I can think of the annealing or the stability of glasses as forming an axis along which for different degrees of stability or annealing, I'll have very different, qualitatively different kinds of yielding behavior. And, many of us working on this see this as a paradigm with which to understand, in fact, the diversity of yielding behavior that one sees in many different glassy materials. Okay, so now, so here's a quick summary, the first 3 points of what I've already said. Of course, what I told you just now is bad for materials engineering, because it basically says a better annealed glass is a brittle glass. Nothing you can do about it. But there are interesting new ideas that one can think of. One way is to not take a homogeneous glassy material, but to embed in it what are called inclusions. Materials, you can think of making a glass out of atoms ABC, in which you put nanoparticles made up of D. Okay, and this kind of tricks can then modify the yielding behavior, and many people, both theoretically and experimentally, are exploring this. Okay, that's work in progress. Okay, so I think I've sort of exceeded the time that I have, but I was told I should also give some kind of an outlook and opportunity kind of summary. So let me quickly go through these points. Now, unlike the previous talk where there were sort of very concrete problems which offered both challenges and opportunities, I'm going to sort of talk a little bit in the abstract and also in terms of ideas and methodologies. So if you look at sort of theoretical and computational investigations of the behavior of materials, a constant and in fact open avenue is the search for new organizing ideas and new approaches. So what I presented to you about glasses is an example of something that happens in a variety of different ways in different materials. But there's also interesting computational challenges, okay? So with the increase of computational power, we can do a lot of things that we couldn't do a decade or two ago, but there's still a lot of things we simply can't do, okay? A major challenge in computational sciences is the simulation of systems with complex landscapes like glasses, but also a variety of soft materials, polymers, for example, and biological material, chemical reactions. So there are lots of them where the issue is that we face is what one might call the time scale problem. We have to do simulations for long enough, and often we can't do long enough in a simple-minded way. So there's always a challenge of developing and deploying new methodologies to overcome this time scale problem. And in these days, there are also sort of questions that come up because of new tools that have become available. Machine learning is something that people are using in a variety of contexts, including understanding some of the problems that I talked about. I won't have, of course, I won't be talking about them, but also maybe much more commonly known are methods for designing new materials with desired properties, targeting self-assembly processes, etc. I already mentioned something about materials development. And now the last 2 points, one on this slide and one in the next slide, I want to sort of focus a little bit on. Physics has always thrived by seeking and seeing analogies between problems in distinct domains. Okay, so one thing that's pertinent to what I've talked about is, in the last decade or a little bit more, a lot of biological systems have been usefully thought of as soft matter. And lately, a lot of their behavior is also being analyzed through the prism of what we understand about glassy systems. Okay. Now, in order to do something like this, it doesn't help to be a very narrow-minded specialist. Okay. There has to be a certain perspective about how you see your research, and that's, let me come to the last slide. Doing research necessarily tends to be, an act of specialization. You pick one particular system, one particular method of study, but it's very, very important when you're certainly when you're learning to do research, to keep in focus the idea of not being too specialized in what one pays attention to. It helps to sort of have one's tastes and dislikes at the level of broad domains. You may like how statistical physicists approach a problem as opposed to solid state physicists, though that's sort of splitting hairs. But having sort of made one's choices at that level, one should really try to get into the spirit of how a certain kind of physicist goes about solving problems, what kind of tools they use, and what kind of methods they use, what kind of paradigms they think in terms of, and be flexible, or learn to be flexible about how those ideas and methods can be employed for any problem that you might end up looking at. Okay, it's very important to have this perspective that you can see the same problems appearing in many different places in different guises. And it is often very advantageous to be able to see those analogies and solve problems for which one doesn't know the answer by using methods which have already proven successful. Okay, so with that I stop. I'm sorry I ran out of time a little bit. I'm happy to take questions.
No, absolutely fine, sir. I was expecting 4 to 5 minutes extra itself. Would you like to take up the questions by yourself, or shall I read it out for you? If you'll just stop presenting, then you can see the Q&A.
Okay, yeah, now I'm seeing it now.
Okay, fine. So you can take up the questions the way you would like.
Questions which were meant for the previous speakers, which I have to get.
Yeah, you have to scroll down. Yeah.
So, so shall I? Yeah, I don't mind just going through. And so first question, I guess, is how are amorphous solids held together? They're held together by the same forces that hold together crystalline solids. It's just that the arrangement of atoms is different. They do have attractive interactions typically, though not always. But how they're organized in space are very different. And this leads to the differences in properties that I mentioned. Okay. Can all compounds be converted into classes? Yes, the answer is yes. But there is, how easily you can do it is very variable. So roughly speaking, if the speed with which a material will go into the crystalline state is high, then it's very difficult to make a glass out of that. So if you have just a like if you have iron, a melt of iron, and you cool it down, it will probably always make a crystal because it's easy to do. Whereas if you take some very messy organic molecule with 3 benzene rings and so on, that will probably more easily make a glass. Okay, but in fact, the metallic glasses that I talked about, it was actually something of a breakthrough even to just make them, because they're all they're all atomic glasses. But the trick that is used is to combine 3 or 4 different atoms, 3 or different elements. So by using various sort of insights into how you mix these different elements, you can then begin to be able to make these alloy glasses. Okay. What are the different applications of spin glasses? Okay, well, you know, I would, as I tried to say in my talk, spin glasses, of course, they're interesting magnetic materials, but the real application has been the theoretical developments that have been used to study spin glasses, having found many applications in everything from computer science to, you know, machine learning to how you think about protein folding and so on. So spin glasses as materials have been less successful than spin glass theory. Okay. Now, how spin glass is different from spin liquid? Okay. Well, basically, okay, the strictly speaking, you know, one doesn't talk about something called a spin liquid, but if you think about magnets, all magnetic materials at high temperatures have what is called a paramagnetic phase, okay, which is the equivalent of the spin liquid. So spin glasses, again, like other magnetic materials at high temperatures, has a paramagnetic phase where if you look at the magnetization versus magnetic field curve, it'll have a single branch that will be roughly linear for small fields going through the origin. But all that changes when you go to low temperatures, where you have this distinct phase called the spin glass phase. Okay, what's the relevance of spin glasses in biology? Well, okay, historically, the example that I just mentioned, it's not a direct application, but if you think about the problem of protein folding, the people who worked on these theories in the beginning made analogies with what happens in spin glasses. So it sort of provided the language in which to model and think about protein folding. But you know, the ultimate picture of protein folding doesn't particularly involve spin glass physics. Okay, but glasses more generally are very useful in thinking about biological systems, because whatever you form in biology, by and large, is soft and disordered. So glass physics is much more broadly relevant in biology. Okay, which compounds make best glasses for their use in food industry? Aha. So this is an interesting question. I don't think you should ask the question this way, because the main concern of the food industry is to make something that you can eat. So it's more the question has to be, you know, how do you use those same ingredients to make them last longer, and can glasses help? And the answer is yes. Basically, a lot of the research that people do in this regard, you know, in terms of food preservation, is focused on how to make whatever food that I'm making remain glassy rather than crystallize. So one of the key concerns, if you make ice cream, for example, you don't want the water in the ice cream freeze into ice, because then it's terrible. You want, even if it goes into the solid state, you want the ice to be you want the water to be in a glassy state. So sort of the workhorse system that people have studied a lot is sugar water solutions. So you can ask the question like, how much sugar do I need to have in water to make it a glass easily? Okay. Okay. So, you know, reading the questions and answering is very easy, but you have no idea whether you're answering to the questioner's satisfaction. So if by the time when I go through all the questions, if there are further questions or questions that I didn't answer satisfactorily, you can feel free to add. Is bioglass different? You know, I'm not really sure what that means. Like I said, there are a lot of biological systems and assemblies which are glassy, but I'm not sure what bioglass particularly means, but maybe if you tell me, I can answer. So slow cooling of liquids leads to quenching to glasses, and fast cooling gives rise to... No, that's not quite right. I would like to know whether the second process is the annealing one. No, sorry. You can make glasses either by slower or faster cooling, but if you cool very, very slowly, you will make a crystal. But there's a range of cooling rates for which you can make a glass. And the slower the cooling rate is, or lower the cooling rate is, the better annealed the glass will be. Annealing means that. Annealing means changing the temperature slowly. Would you please give us some examples of glasses? Those are actually made up from structurally arrested states. Okay. No, any glass, like window glass, is a structurally arrested state. What that means, that phrase structurally arrested, means that, first of all, once you form the glass, you can look at sort of the atomic positions or the relative atomic positions for long times, and they don't change. That's what structurally arrested means. And this is in contrast with what is happening in a liquid where particles are moving around. Okay. And now your silica glass is a structurally arrested state. You know, if in equilibrium, it should form quartz or beta cristobalite or some kind of crystal, but it doesn't. And so it sort of gets frozen in this disordered liquid-like structure, and it stays there. And that's what structurally arrested means. How liquid crystals differ from glass? Okay, very good question. Liquid crystals are actually a very distinct category. First of all, they're fluid. They're called, the crystal part of liquid crystals comes from the fact that the molecules that make up liquid crystals show order in the form of alignment. Okay, but they do move around. So they're very different in that sense. They don't have the fundamental property of rigidity, in the structural rigidity. Yeah. Please repeat the second question. How amorphous solids are held together. Let me come back to this. So give an idea of how spin property can store data or transmit data for different types of solid state memory devices. Okay. Well, okay, the spin property that is used in magnetic memory devices is fairly straightforward. If you go below the ferromagnetic transition temperature, the spins are all going to be aligned, so they'll have a net magnetic moment which can be detected. And you can also align that magnetic moment in different directions by applying field. And so that's how a magnetic memory device works. Now, one of the examples that I had mentioned of a memory device is it's called what's called a phase change memory device, where you use this property of the final state of the material being either a crystal or a glass, depending on how fast you ramp up the temperature, to basically selectively make a bit of this memory device be in a glass state or a crystalline state. So these are called phase change memory devices. Okay, that's different. Their spins are not directly involved. Now, how amorphous solids are held together, I am not sure if I have a very different answer than what I already gave. If you have interactions between atoms which are cohesive, you will, under suitable conditions, basically low temperatures, you will form a solid state. And if the atoms come together in a regular assembly, you get a crystal. If they come together in an assembly where the atoms are not in periodic positions, then you have a glass. Okay. In both cases, they're held together by whatever attractive interactions you have. On the other hand, the attractive interactions are not absolutely necessary. Okay. So there are many examples where by restricting the density of a given material, even in the absence of attractive forces, you can make either a glass or a crystal out of them. But the physics of that is a little bit more complex to explain. So let me not try that. But the next question, how can we make bulletproof glasses more economically? Can you explain the structural property of bulletproof glass? How is it different from normal glass? Okay. In fact, can I show an extra slide which I didn't have time for? This is, in fact, okay. How do I go slide? Just give me 1 second. So this is an idea. I don't know how much it's actually been put into place, but there is a related phenomenon to what I've been talking about called jamming, and which is basically the phenomenon that if you take granular matter like sand, if you compress them, they sort of jam up, meaning they become solid-like. And so one of the ideas that people have explored is to take Kevlar fabric, which is some kind of polymeric material, I believe, but you put a suspension of grains, small millimeter size, let's say. And there, in addition to the fabric itself, when you try to stab, or when you apply a force very fast, the response on those short time scale of the suspension that you include will be solid-like. And so this makes it a better.
One of the biggest unsolved problems.
Sorry, I didn't mean to do that. Okay, so that's one answer. I don't know if it's, I imagine it is much cheaper than making the standard bulletproof materials, but I don't know how cheap. Okay.
Okay, I think you have taken up all the questions, I suppose.
Yeah.
Yeah, fine. Thanks a lot, Professor Sastry, despite of not keeping well, having a sore throat, and you told me before the lecture itself, but you have taken up all the questions to the satisfaction. I can see the comments, the compliments which I am seeing in the chat section itself. So that shows that it went out quite well. And before I conclude the session, I would like the convener of the program, Professor Anurag Sharma, to kindly say a few words.
Yeah. Okay. So we have come to thank you, Dr. Sastry, first of all, for an excellent talk, quite engaging. So now we have come to the end of this 6-day program that we had started on Monday, and Monday or Sunday?
Yes, Monday.
Monday. Yeah. Today is Saturday. Yes. So we had 11 talks by eminent speakers in variety of subjects. As I said on the first day, the whole idea is to bring the interdisciplinarity of science and engineering to the fore, and to expose the participants to variety of subjects, and see the connections, if any, with what they're doing, so that they can have a cross fertilization of ideas. So we had talks by, I'll just sort of would like to thank all the speakers one by one. And Professor Jitendra Khurana and Dr. Dinkar Kanjilal spoke on the first day. Then it was followed on chemical sciences by Professor Anunay Samanta and Professor Saurabh Pal. Then we had on the third day a computer science talk by Professor R.K. Shyamsundar, which was followed on the fourth day by on biological sciences by Dr. Anurag Agarwal and Dr. Rakesh K. Mishra. Then we had mathematical sciences on the fifth day, that was yesterday, by Shekesh Gopal Rao Dani and Professor Praval Chaudhary. And of course, today we had talks by Professor Ashok Kumar Singhvi and Professor Srikanth Sastry. So as you can see, we have covered physical, chemical, biological, mathematical, computer science, all kind of subjects in these 6 talks. Of course, the conditions today and this online format made it possible that we could meet for 2.5 hours every day in the evening. In a physical mode, that would have not been possible to bring people every day back for the talks of 2 talks. That would have been probably all these talks would have been covered in 1 day or 1.5 days, which would have been a little more heavy than this format. So technology does bring some positives to the fore, and I'm sure the participants, as the I think Manoj Saxena will give you some details a little later, have been, their sustained presence has shown that the talks have gone very well, and they have kept the interest of all the participants. So I'd like to thank all the speakers. 2 of them are here today, others in absentia. I would like to thank all of them, and it was really a good success. The format, which I'm sure Manoj Saxena with his friends had evolved, is really worked out very well. So thank you all. And so Manoj, over to you. You want to give some details about participation?
Sure, sir.
Yeah.
Sure, sir. I think my screen would be visible to all of you.
Yeah.
Yeah. So this program, which was spanned over the 6 days, so big thanks to Professor Anurag Sharma, who conceptualized this program along with me. And as a statistics, this is important to share that average attendance every day was around 250 plus. It ranged from 240 to it went up to 300 like today itself. And if I talk about the distinct individuals who have been there all throughout 6 days in 1 or 2 sessions, or maybe more than that, has been 800 plus. And especially the participation is not only from India itself, it is from outside India, Nepal, Australia, Cambodia, Hong Kong, USA, Brazil, Argentina, and so on. And so like it has already been told that eminent speakers have been participating in this particular program. And this was the technical program schedule which I have shared. So the very first day itself, we had talks by Professor Anurag Sharma and Professor Khurana and Dr. Kanjilal. I've tried to give a breakup of the number of attendees who were there in each session. And then on the bottom left-hand side, you can see the total number of attendees from India and from outside India. Then the second day with Professor Samanta and Professor Saurabh Pal, the average attendance has been crossed 270, and the number of attendees from inside India, it's about 360, and outside is 15. And the third day, Professor Shyamsundar's talk was there, and there again, it was well attended by over 290 plus attendees and an average. But if I check the records from the Zoom itself, it was more than 350. Then it was a very excellent talk by Dr. Anurag Agarwal and Dr. Rakesh Mishra on the day 4. Both of them, the CSIR directors, they kindly agreed to deliver a talk, which was attended by an average 275 attendees, and more than 360 in all were benefited on that very day itself. And then yesterday, it was on day 5, Professor Dani and Professor Prabal Chaudhary took up the mathematical science section and explained the concepts are related to and the contributions of Professor C.R. Rao by Professor Chaudhary, and it was very well taken. And today I've just taken some data from the Zoom itself, and in the very last session itself is about 300 and started with 260 to 300 attendees were there. And so big thanks to the 3 academies, the Indian Academy of Sciences Bangalore, the National Academy of Sciences Allahabad Prayagraj, Indian National Science Academy INSA, my host institution, the Dayal Upadhyaya College, the Department of Biotechnology, under whose benign aegis we are organizing these workshops under the DBT Star College program, Professor Anurag Sharma, and my team members, Dr. Poonam Kasturi, Ms. Shweta Vadera, and Dr. Gitika, who have been there with me all throughout, right from conceptualization to during the program itself, for sending emails and motivating students and faculty members to be part of this program. And so on behalf of the organizing team of Dayal Upadhyaya College and the National Academy of Sciences India Delhi chapter, I would like to invite all of you to kindly do attend the special public lectures which we are organizing in next 15 days or so. The first one is on September 21st by Nobel laureate Professor Jean Merlin on steps towards complex matter chemistry, and then on September 22nd by Carmen S. Manoni, who's the president of IEEE Photonics Society. And then October 6th, we have another talk by Nobel laureate Professor William D. Phillips, who will be talking to us on a new measure, the reform of the international systems of unit. So I'll be sending emails related